is what makes turbulence hard. And we can guess the outcome. Out of complexity comes a simple picture of scaling varying cascades, which isn't the whole story. So what I'd like to do now is going back to 1883, to the first scientific studies made by Osborne Reynolds in the late 19th century. So here you see his apparatus. It's a pipe, and he was interested in the flow of fluids in pipes. He was interested in everything, but this is where he did his controlled experiments. So he had a reservoir here, he sent in water through here, and then he observed what happened as the water flowed through this pipe, and he watched it very carefully. What he realized was that what happens, what you see, depends on how fast the fluid is going. But he also realized that it doesn't just depend on that, it also depends on the viscosity. Because if you have a fluid that is not very viscous, say like superfluid helium, you only have to push it a little bit, and it will immediately become turbulent. If on the other hand you have a fluid like honey, you have to push it, make it go really, really fast before it will become turbulent. So he realized that there's a number that you can define, which is now called the Reynolds number, which is defined in this way: the flow speed times the system size, let's say the diameter of the pipe, divided by the viscosity, also divided by the density. Okay? So that number it has no dimensions, it's just a pure number, and it tells us every fluid you can assign, if it's in motion, you can assign this number to it, and what that number is tells you whether the fluid is going to be behaving well or whether it's going to be behaving badly. So what he saw was when you changed the Reynolds number, somewhere around 2000, he saw these things called flashes of turbulence. I want to tell you a little bit about those flashes of turbulence. We call them puffs today, but what they are basically is here the fluid is perfectly laminar, everything's predictable, and then here's a bit where it's completely chaotic and turbulent, and you don't know what's happening, then laminar again, then turbulent, then laminar. So the way the turbulence arises is this alternating pattern of laminar and turbulent flow. So let's just go back and think about what that means. So here's our classical fluid, this was our honey, the velocity can swirl as slow as you like. Here's our quantum fluid, superfluid helium, where you can't swirl it slower than a certain amount. And this is laminar, this flow is typically much less than 1, whereas it doesn't take very much effort to make superfluid helium have a Reynolds number of about 1 million. Very turbulent. Okay, so here is a map of fluid flow. Every phenomena you encounter in the flow of fluids, you can put somewhere on this map. And the nice thing about this map is it's only one-dimensional, it's only a line. So it's much simpler than the two-dimensional Google maps. The Google map of turbulence is one-dimensional, okay? So Reynolds number being very large, let's say close to infinity, is pretty much what describes a turbulent fluid, like turbulent superfluid helium. So this is where you would get that scale invariant cascade in fully developed turbulence. Somewhere down here, where Reynolds saw his flashes, that's somewhere around Reynolds number 1800 to 2400. If you work in experiments or you do observations of the Earth's atmosphere or something like that, of course the Reynolds number can never be infinity. But it turns out that this picture of the scale invariant cascade still works, even down to fairly low values of the Reynolds number. It doesn't have to be just at infinity. You can be at some medium value. So most of our understanding of turbulence comes in this kind of crossover region here. This is where you are. Okay, just about here, right around 2000 or so. That's the Reynolds number for the flow of blood in your heart. Okay? Now, it's rather unfortunate that you're here, because right at that point, that is where Reynolds saw his flashes of turbulence. And when you have those flashes, alternating turbulence, laminar, it's shaking things up a lot. And it can shake things up so much that the fluid goes through your blood vessels that it can burst them. The fact that you are in this transitional range of turbulence, where this transition is happening, the shocking behavior between turbulence and laminar, that can disrupt your arteries and give you aneurysms. And people die from this. So yes, turbulence can kill you. Down here, in this range 1800 to 2400, that's where all the people who are at the KITP workshop right now, that's where they're all working. Okay? Usually at KITP when you have a workshop on turbulence, people are more or less arguing about what happens up here. But this time, we're arguing about what happens down here. So there's two real questions that one can ask about turbulence. As a physicist, I told you, we like to ask questions that have simple answers. Okay? Like the Kosterlitz and Fowlers did in their Nobel Prize winning work. They took a very complicated problem, and then they asked, does this very simple model capture all the features that we want to see? Well, we can't expect that to work for every single phenomenon. But if it doesn't work, well, that's too bad. But you should always look for that kind of simplicity when you work on a new phenomenon, because that's where you're going to be able to make progress. So you expect to be able to make progress up here, and you expect to make progress when there's transitions. And that's why people now are working on studying this thing here. So the two main questions in turbulence, I would say, is there universal scaling behavior in fully developed turbulence? In various varieties. Some people study just pipe flow, some people study fluids heated from below, so you get convection, some people study fluids going around in between cylinders, some people study channels, some people study jets, some people push airplanes through fluids. There's many different ways you can answer these questions. The second question, and the one that we're going to talk about now for the next 11 minutes and 34 seconds, is how do fluids become turbulent as you increase their flow speed? That's what we really want to understand. How does this thing actually happen? And the answer, I'm not going to be able to tell you the whole answer because it's highly technical, and also we are still debating it, but we've made a lot of progress. We've made a lot of progress because not of theoretical physics, but of experimental physics. Okay, so we have to remember this. Okay, theoretical physics is wonderful, but the primary way that we discover things about the natural world is by doing experiments. So what happened was in 1883, Reynolds did his measurements of turbulence in a pipe. By 2008, Björn Hoff and collaborators did a highly precise measurement of the laminar turbulence transition in an incredibly beautiful experiment. What they did was they took an apparatus, basically like Reynolds's, but much longer, and they put the fluid going in, the fluid comes out the other end, and the fluid just comes out following the yellow trajectory like so. They asked a question, that's a new question. They said, what is the probability that if I make a little bit of disturbance over here, create artificially a little bit of turbulence, what is the probability that it will survive until you get to the end of the pipe? It's a different kind of question. Okay, the sort of question that people had only just started to ask around about this time. And what they realized was this. They make a disturbance, the turbulence goes through the pipe, but maybe the turbulence will die. Maybe you're below the transition to turbulence, so if the fluid wants to be laminar and you try to make it turbulent, the turbulence will eventually die away. If the fluid wants to be turbulent, then when you kick like it to be turbulent, it'll just stay turbulent. So what they wanted to ask is this: as I have a laminar fluid, a fluid that doesn't want to be turbulent, how long does it take for the turbulence to die? And does that time get bigger and bigger as I get closer and closer to the actual transition to turbulence? Because when the fluid is turbulent, you make it with the turbulence, it will live forever. When the fluid excuse me, when the fluid wants to be laminar, below the critical Reynolds number, you make some turbulence and it will eventually die away. So the question is, how long does it take? And so what they did was they measured the fluid as it came out the end there, and if the turbulence was still there, it would follow the red trajectory. It would be slightly, there'd be more drag, because turbulence causes drag. Turbulence makes things go slower. Turbulence is why when you can, if you want to save energy, if you drive your car at 50 miles an hour rather than 70 miles an hour, you actually save double the amount of energy. The frictional drag goes down by half. So what happens then is then they can measure, they ask a simple question: did the puff survive or not? Yes or no? Yes or no? Many, many times. Repeat this many times, and then you can work out the probability that a little bit of turbulence will survive. Now, when they did that, they found an amazing result. This is the logarithm of the lifetime of the turbulent puff, and there's a picture from a computer simulation that Mark Vila did. And the lifetime of this puff is plotted here as a function of this number that Reynolds came up with, the Reynolds number. So as I told you, the transition is somewhere around 2000, 2100. And what you see is that the data show that this lifetime does indeed increase from 100 in whatever units these are, up to 10 to the 8 by the time they got to somewhere over here. The lifetime goes up enormously fast as you change this number. And in fact, it goes up with a functional form, which is really unprecedented. It goes as e to the Reynolds number, for those of you who care. A very, very rapid rise in the lifetime of turbulence. What happens is it kind of splits into two. It makes two puffs. And those two puffs go along, and then I decay, or maybe that splits as well. So you get a very complicated pattern of the behavior of the flow in this machine. And you can measure the lifetime between puffs splitting, and you can plot that, and you get a graph like that. And that's what we Bjørn Holt discovered in 2008. Now I want you to forget everything I told you for the last 45 minutes. Okay? I want to tell you about something completely different. Nothing to do with it. Remember at the beginning I told you that I spent half my time studying biology and half my time studying condensed matter physics. Well, I want to tell you about biology. Okay? You didn't sign up for this, did you? You can leave if you want, but don't, because there's a surprise coming. I want to talk about predator and prey. So I'm a physicist, so basically I work in the scope of mechanical approximation. So this can be walrus, this can be shark, something like this. It doesn't really matter what they're called. But this is the predator, and this is the prey. I want you to ask, what happens in an ecosystem where you have prey like this, creatures like this, which are predators? You have an ecosystem composed of all these things. And then you ask, what is the fate of that ecosystem? What can happen? Well, let's think about it. Let's suppose that the prey birth rate is high, so somewhere up here. So that means that these rabbits, because they are rabbits, right? These rabbits are breeding like crazy. If they breed like crazy, it means that this thing, whatever it is, what is it actually? Lynx or something. Yeah, there's lynx will have enough food to eat, so the lynx population will also grow. And what can happen is that they can come into some kind of balance. The more prey there are, the more predators are, but then the predators eat the prey, so the prey population goes down. And so what actually happens is the population actually oscillates in some way like that. It's not actually trivial to prove that it oscillates, because that's another story, it's something that we work on. But you can show that at a high enough birth rate, this population will be stable, so you get coexistence of both predator and prey in some kind of happy equilibrium. Not happy with predator, unhappy with prey. On the other hand, let's suppose that the birth rate of the prey is too slow. They don't make enough babies. So what happens is the predator eats the prey, and then there aren't any more foods for them to eat. So they start, they go extinct, and then the prey eat them, and they go extinct, the whole ecosystem collapses. It's possible that can happen. And there's a particular point where the birth rate is just low enough that the ecosystem suddenly starts to become stable, and for the prey and the predator to coexist. So how did let's do it. Do a simulation of a predator-prey ecosystem. It was out of we had a new ecosystem to study for, because we did some experiments, but let me just tell you this surprising thing. You start off with predators and prey, and you vary the birth rate, and you ask the following question: as I change the birth rate, how does the lifetime of the ecosystem change? This is the ecosystem that we simulated. Here is the prey. We're just showing you prey here. There's prey and there's predators elsewhere. And you look at the patterns of the prey over a certain amount of time, and it also makes the same structure. This pattern here, you analyze this pattern, and it's very fractal. This pattern has very interesting geometrical patterns, and they show the same kind of scaling and cascade behavior that I talked about before. Just like that. So why the turbines look like ecology is because they will, when examined in the white paper, make this pattern, this geometrical pattern in space and in time, and that's going to make it perfect. Alright, so what did you want to do? Well, I told you that turbulence is an unpredictable, complex flow. It's going to provide radial landscapes. I told you that in a valley, the flow runs on the edge of turbulence, and crossing a transition equation. For many people, certainly here at this workshop, I can now measure the transition very accurately and quantify its behavior. And there's analogies between what happens in turbulence to other fields in science, like the extinction transition in an ecosystem, percolation, the scattering of high energy elemental particles, and also, in fact, it turns out that the behavior of just the signals in nerves, that turns out to be related to what happens in turbulence. So here's the people who did the work I showed you. This is Ian and me standing next to Reynolds' original experimental apparatus. It's still on display at the University of Manchester in England. You can go there and be a scientific tourist and stand next to this apparatus. This is in a solid place in Manchester, England. What is the take-home message I want you to know? However, physics starts with a simple guess, but the exact equation is too hard to solve. This whole thing happened in participants, and I guess we experiment, and the experiment suggests new guesses, and so we have this virtuous cycle of experiment and theory. Simple models, they look too simple, but still very, very simple, can describe very complicated phenomena. Why is physics so successful? Okay, it's not because physicists are smart nowadays, okay? It's because we work on simple problems. Okay, we choose problems to be simple and easy ones, okay? Biology, much harder than physics. Economics, much harder, okay? So we don't really know to what extent the physics approach can be used in more complex sciences like biology. We discovered that it can be used in some cases, maybe not as much as we would like, but perhaps more than you might have expected. And the problem turbulence is not solved, but we certainly understand a lot more than we might today, thanks to brilliantly controlled experiments and healthy interactions between experimenters, theorists, and computational physicists. But I want to end with a comment. This is a fortune cookie that I got. Now think about this. There's something serious here, okay? So usually it's the case in science, particularly in physics, that physics, physicists, is applied to some like, for example, the Nobel Prize in into wavelength by assuming that the time and space are related in some sort of way. So basically, you can, most of the time, you measure the speed of the wind, you measure the wind, measure the fluctuations, and then you know where the fluid is flowing. And I'm measuring the fluctuation here, related to here. So that's how you can work out the spatial part of it. Effectively for the PSD. The PSD. Yes, that's right. Exactly, that's right.
So on the Reynolds experiment, there were little puffs.
Yes.
Are those standing puffs, so they're individual particles that are moving through an area of turbulence, and then they become stable, and then they become turbulent, and the same particle becomes stable? And if so, can those areas of turbulence be predicted?
That's a really, really good question. So you might think, looking at those puffs, that they're just moving along with fluid, okay? And they're not. Okay, you're asking, is the fluid moving through the puffs coming into the shore? The fluid particles actually go around in circles like this, they're not crowded like this, but the net effect is this way. It's kind of like that. It's like motion. Those puffs move slightly slower than the rest of the fluid. And actually, we don't know. We don't really understand how to predict that. I think it's a very important clue to try to understand the things that we can't fully grasp yet. And to keep working on this, I'm not really focused on that aspect, but it definitely is like that. When we do computer simulations, you move at the same speed as the fluid, you can see these puffs going backwards, but we don't really understand exactly what they are. So thank you, very good question.
I'm not sure if I got this right, but I thought I saw a graph where you had turbulence cascading and terminating in viscous flow.
Yes. So